The Pacman tournament was a challenging problem because it involved many variables on both the offense and defense side. We had three agents that reliably beat the baseline agent by a comfortable margin: the UCT agent, the exhaustive simulation agent, and the approximate Q-learning agent. The UCT and approximate Q-learning agents utilized a fairly standard implementation and are discussed further in the wiki.
This approach started off in the intent to implement Monte Carlo tree search, but took a turn and I implemented random simulation as it showed promising results. Both our agents are set to go all out offensive. The features and weights used in this approach were not optimal and could have been made better. This algorithm takes all possible actions into consideration and generates a game state. From this, a finite number of random actions are generated and a value is calculated for this game state. The maximum value is the favorable action and it is returned. There arises a conflict where the evaluated values may end up in a tie for different features and the agents end up looping. Improvements could have been made by tracking the actions or by improving the weights to avoid the looping.
We had considered value iteration as one of the algorithms to implement in this project. However, as I will explain, we had to drop it in favor of other algorithms. Firstly, we will give an overview of what restrictions we had to work under. The first restriction that we had was that we had a time limit that had been forced. As a result, we had to return an action within a time period of 1 second. If we exceed this time limit, we will be given a warning. 3 such warnings or returning an action that takes more than 3 seconds to be returned ends in the game being forfeited. Another restriction that we had to work with was that the state of the game was being changed at every turn, and due to this we could not train the algorithm beforehand, as the values v of s are determined based on the state of the map during a turn. Now we will show the execution of the first design approach that we considered for value iteration. The first one was where we took a subset of the map and performed the required calculations on the location cells that were extracted from the designated area. What is happening here is that the aim of the agent is trying to reach the half line, after which it will turn into a Pacman. The way the action decided is by getting cells of 2 columns ahead the agent and 1 column behind the agent. We are taking the single column as well as so that if the agent needs to backtrack, it has the ability to do so. In a short while, we will see the first problem that our implementation has. Basically, we had to solve many such cases individually, which further complicates the implementation and is prone to introducing more errors. As you can see, the agent skips the foods that were close to it when it should have eaten those. This is caused because after every turn, the agent looks for the closest dot from the current location, but also since we are handling some other cases that cannot be planned ahead. Now we will discuss the other approach we tried, where we were taking the whole of the map into consideration. As you can see, the calculations do not complete within the 1 second time period, and that is a huge problem.
The exhaustive simulation agent evaluated every possible path of length 4 from the current position with a fixed upper bound of paths of 4 to the power 4 paths evaluated. For UCT and exhaustive simulation, we used path length to determine the terminal condition, but the major challenge was figuring out the rewards to backpropagate. For approximate Q-learning, the challenge was also to determine what the shape reward should be, as well as playing enough games against a variety of agents to get the weights to converge. We mostly played against the baseline exhaustive simulation agents. We faced some difficulties in deciding which agent to use for the tournament. Nightly results were not very indicative of future performance because many new agents entered every day, and people were trying different approaches as well. We decided to pit the agents against each other, and unsurprisingly, the UCT agent performed the best. We did face a number of problems with this evaluation, especially on bottlenecked maps, as the agents sometimes got stuck in the stalemate loop around the middle. The UCT agent had a number of advantages in theory over the exhaustive simulation agent. It is an online interruptible algorithm, and it weights moves based on the best predicted outcomes from that move, due to the exploitation leading to a higher number of visits to better children. In comparison, the exhaustive simulation agent visits each child exactly once and gives a simple average, potentially missing out on better moves. The Q-learning agent performed very well while training against the baseline agent, but was unable to learn weights to beat the other two agents within the time we had. We originally decided to submit the UCT agent since it performed best in head-to-head testing. However, we submitted our Q-learning agent on the last extension day, when most teams would presumably have been fielding the final agent, and it surprisingly ranked above the top staff team. We therefore decided to leave the Q-learning agent as a tournament agent on the basis that it performed the best empirically. If we had more time, some of the changes we have made included simulating enemy moves instead of assuming they were static, trying to optimize parameters, and trying different methods of speeding up queue learning.